Hello everyone. This video is about BJT structure, bipolar junction transistor structure. Before going forward, I would like to revise what we have done before. Uh, in the previous chapter, we have already talked about diode, the diode structure, and also the current, the diode current. And we know that the current of the diodes I is given by the I is equal to I Z and then times a bracket of expression. Uh, and then the I Z is given by the cross-sectional area times the electron charge. And then the intrinsic concentration square. And I will just say Ni is the intrinsic intrinsic atoms concentration. The square of Ni and then multiplied by a bracket of expression. Dn is the electrons divisibility. Electrons divisibility. Similarly, dp is the whole divisibility. And Lp is the diffusion length. Of electrons. And the rest is similar, yeah. Lp, right, the diffusion length of the holes. And in this case, the diode is very simple. But what if we heavily dope the N region? Now, you have a region here. We have a special diode here. The N region here is heavily doped. According to this equation, if the N region is heavily doped, then this term will be trending to zero. And in this case, I would say if the N region is heavily doped, then the reverse saturation current becomes I Z A Q N I square and then DN LN and then NA. Yeah. So basically the terms is almost independent of the expression here is almost independent of the concentration of the N region, the N plus region. So now you know that right under this condition, the current IB is given by IZ and then now what happens if we make this layer as thin as possible? Well, what if the P region is ultra thin. So when this layer is very thin, the transfer, so now electrons in this region is the majority carrier. Once they step into the P region, it becomes the minority carriers. The minority carriers are subject to recombination. When it is the case, then the minority carriers will eventually become neutral. It becomes one of those. It will become replaced. So there will be no more minority carriers. And how this is the process of weakening the diode current. So what if we make this layer very thin according to our analysis here? The P regions, uh, the P regions, the trans of recombination. In the P region will be less. Now let's try this. We do this, make it as thin as possible. Let's say, like, so thin to this extent. And this is P, and this is P. Then theoretically, with less chance of recombination, users have a lot of column, but unfortunately, it's also up to the area of the base region. It's also also depends on the geometry of the structure. And another thing that we are going to do is to capture this column instead of having the base to collect all the collector. Instead of having the base terminal, the B terminal to collect the diode current, we try to do it differently. We do this, we add another layer, another region. And this region is also an N region, but not N plus region. The concentration, the doping concentration in this region is substantially less than this and that. So if this is the case, then we should be able to capture the current. If the junction here is a reverse bias, if the junction here is under a reverse bias, then the current here, I tell you what, if this region is thin, the chance of recombination is less. And another chance of the electron going straight through is higher due to the process of electron punching through. So due to the process known as punch through, the electrons from the N plus region just go straight to another N region here. And let's call this region collector, because this is what was intended. If due to the process of known as punch through, the electrons in from the from the N plus region. Go straight to the collector. So basically, all the electrons just go straight to this region here. So the end result is you have a substantial current here. And this is the end result is the current that you originally expected to collect. The diode current will become the current of the collector terminals. So instead of having this equation, the end result will be IC and then IZ minus 1. So basically, it's just a modified diode. Originally, in the two-terminal diodes, the current and the voltage are shared. And the voltage input also depends on the current across it. And sorry, I should say that the current also depends on the voltage across the junction. But now we are trying to collect the current not from the voltage terminal. Instead, we do it through another terminal called collector, and we collect the current of the diode here, and that's how we end up with the expression very similar to the original diode's characteristic. This one. The only exception here is the current becomes the current of another terminal, not become B, not like this here. So this is what happens in this kind of device, because of this characteristic, we can plot this in a graph. So at least we have some kind of modified diode characteristic. Modified in the sense that the current in the C terminal becomes somewhat like the diode current. The voltage here will be controlled by the so-called VBE and VBE with different base emitter voltage, you will end up with different current. If the voltage is too low, lower than the built-in junction voltage, then there will not be any current. And this is the so-called cutoff. And if the base emitter junction has enough voltage, say slightly higher than the base emitter voltage, slightly higher than the built-in junction voltage, then you will have a substantial current gain. Ideally, right, we expect this region to be almost vertical, but because of the length here, because of the voltage here, it depends. it depends. It depends on the voltage between the collector and the emitter. And ideally, when the collector, when the VCE is high, then we will have more ideal characteristic. But when it is low, then we will have less than ideal characteristic here, like this one here, this one here. So this is first characteristic, the first phenomenon of the transistor. Basically, this is just a proof that it is just another modified style. But the point is, we are not using the device as a modified style. It's pointless. We are going to use it as a switch, as a linear amplifier. So this is the second point that I would like to introduce to you. And now you have, according to this equation, the collector current will depend on the base emitter voltage. If the base emitter voltage is less than the built-in junction voltage, then there will be no current at all. And if it is larger than that, then we will have a substantial current then, yeah, depending on the base, the collector emitter voltage. Okay, so this is the number one point that we want to highlight. But this is not the main point. The main point is the scientists from Bell Lab have found out another more important characteristic. And if we plot the collector current against the collector emitter voltage, we end up with something very strange. We end up with something very strange. Depending on the base current, if the base current is high, then we will have a flat region here. We will have a flat curve here. Sorry, flat line. And the region here is almost flat. Flat in the sense that the slope here is 0. Is trending to 0. Okay? And this region is so-called the active region, because this is exactly what we want for amplification. So I will just highlight so this region. Sorry, I shouldn't cover this one. This region, right? It is the active region. Let me take a check whether we can read the text. Yes, we can read. And at the voltage, when VBE is too low, then there will not be any current. This means when IB is almost 0, then you will end up with low collector current. And we call this this region with low collector current as cutoff region. And finally, there is another little region here. And at this region, the collector current is almost proportional to the VCE, the collector to emitter voltage. So in this region is just the ohmic region. Again, this is just useless. And this region is so-called saturation region. It's a useless region. The only region that is useful is the active region. So far, right, this is the main point of these lessons. If you have any question, please leave your question to the comments box of this video. Thank you very much.